We're going to begin by comparing and contrasting the properties of acids and bases. So acids contain more hydrogen ions than hydroxide ions. Going back to the nomenclature unit, this should make sense because acids begin with hydrogen. They have a pH of less than 7. They taste sour. They will turn litmus paper red. They're going to conduct electricity, meaning they are electrolytes. And they're going to react with metals to produce hydrogen gas, and you'll see that in the form of bubbles being produced. Bases, on the other hand, they contain more hydroxide than hydrogen ions. They have a pH of greater than 7, so they're alkaline. That word alkaline is synonymous with base, so get used to that. They taste bitter and they feel slippery to you. So it's kind of interesting why they feel slippery. This is because they dissolve the fatty acids and oils from your skin, and it cuts down on the friction between your fingers as you rub them together. So you feel like bases are slippery because of this reaction with the oils on your skin. Bases are going to turn litmus paper blue. They're also going to conduct electricity like acids. So this is something they have in common. And bases are going to react with acids to produce salt and water in a neutralization reaction. Some examples of common household acids and bases. So acids are things like citrus juices and lemon juice, tomato juice, vinegar, and carbonated beverages. If you look on your food labels, you'll see that they have several different types of acids in them. Bases, on the other hand, are things like ammonia, drain cleaner, antacids, bleach, baking soda, and your soaps and shampoos, hence why they feel slippery. Okay, so me being me, I have to go on a health tangent here about sodas in your body. So sodas are acidic. If we look over here in the far upper left corner, we'll see the pH of different substances, water being neutral at 7. And as we go down the scale, it gets more and more acidic. So milk is actually an acid. Black coffee, more acidic. Once you get to a pH of 5.5, the enamel on your teeth begins to erode. So Dr. Pepper, Sprite, Mountain Dew, Coke, and Pepsi are really low in pH and will erode the enamel on your teeth. And they cause cavities because they're high in sugar. So it says erosion begins when the acids of soft drinks encounter the enamel on your teeth, which is the outermost protective layer. Their effect is that they reduce the surface hardness of the enamel and make your teeth more susceptible to things like sugar and temperature. So I actually had a kid ask me today in class, Miss Hessel, why do my teeth hurt when I drink cold water? And I asked him, well, how much soda are you drinking? Because if he's drinking a lot of soda, it's possible that he has eroded some of that enamel on his teeth, and therefore they're more sensitive to temperature differences. Other effects of soda are on your bones. So if you look at this picture right here, it says, these are your bones, and these are your bones on cola. The phosphorus actually reacts with calcium and it binds the calcium and then you pee it out. So it lowers the mineral density in your bones and can lead to osteoporosis. So this is actually kind of dangerous. More brittle bones means increased fractures and things like that. Especially with older age, it becomes dangerous when it comes to movement and mobility, etc. And then over here, this one is one of my favorites, premature aging. Phosphate content found in soda is a chemical agent that promotes early aging symptoms, making skin and the muscles wither and look aged. So soda causes you to look older than you are, which is also bad. And I'm pointing these particular things out because they all have to do with the acidity of the soda. In conclusion, drink more water, drink less soda. It's not very healthy for you. Acid-base theories. There's two theories I need you to be aware of. That's the Arrhenius theory and the Bronsted-Lowry theory. So in the Arrhenius theory, these are kind of the standard theories that we've talked about. An acid contains the hydrogen ion, and a base contains the hydroxide ion in the formula. So some examples of those are nitric acid and sodium hydroxide. This is kind of what we learned in nomenclature. The Bronsted-Lowry theory, on the other hand, is different. It defines an acid as a proton or hydrogen ion donor and a base as a hydrogen ion acceptor. That's why ammonia is a base, because it accepts hydrogen ions. And we'll see some examples of that in a second. The Bronsted-Lowry theory includes terminology that we haven't used before, conjugate acid and conjugate base. So let me explain. The conjugate acid is the particle formed when a base has accepted a proton or a hydrogen ion. The conjugate base is the particle formed when an acid has donated a proton. So when you see accepted a proton, think extra hydrogen. When you see donated proton, think less hydrogen. So let's look at our little picture. Okay, so here we have our acid because it has hydrogen and something else, and here's our base. So our acid is donating the hydrogen to the base. That's on the reactant side. Let's look at our product side. What do we have as a result of this? So our conjugate base is what's formed when the acid has lost its hydrogen. So every acid has a conjugate base. Now, the conjugate acid is what's formed when the base has accepted that proton. So when you see a conjugate acid, it'll look like the base with an extra hydrogen. Here are some real examples. This may help a little. So we have our acid here, hydrochloric acid, and it's going to donate a hydrogen to water. So water is acting like a base here. If we look at our product side, this stuff right here looks like water. So it looks like our base, but it has an extra hydrogen. That's a conjugate acid. Then we've got the chloride ion. It looks like our acid, but it's lost the hydrogen. That's our conjugate base. Okay, so go ahead and pause the video. Try the example at the bottom. When you get back, I'll explain to you the bottom example. And okay, welcome back. I hope you were able to figure this out. So if we look at the bottom example, water this time is our donor, and it is donating hydrogen to ammonia. So water is acting as an acid, and ammonia is acting as a base. On our product side, the one that looks like the base but has an extra hydrogen is our conjugate acid. The one that looks like our acid but has less hydrogens is our conjugate base. Okay, next we're doing a quick review of nomenclature on acids and bases. So I'm going to go through this really quickly because we've used this many times in this class already. Okay, so acids. They're composed of hydrogen followed by some anion. Okay, and the rules for naming acids are based on their anion name. So HCl and HF. The anion here is not a polyatomic ion, so it's on the front of our periodic table. When you have your anion on the front of the periodic table, this is a hydro acid. So we've got hydrochloric acid and hydrofluoric acid. Our bottom examples, these are polyatomics. So there's no hydro in the name. We need to remember what I ate was icky and the bite was poisonous. So NO3 and CO3 both end in H. We've got nitrate and carbonate. This changes into nitric acid and carbonic acid, ate to ick. Down here, we've got nitrite and chlorite. So ite turns into us, and we have nitrous acid and chlorous acid. To go from the name to the formula, we need to crisscross oxidation numbers. So hydrobromic acid, you've got hydrogen crisscross with bromine, +1, -1, HBr. Acetic acid, you've got hydrogen and acetate, +1, -1, you can just smush them together. Phosphorus acid, so it ends in OUS, it should go back to ite. So you've got phosphite, so hydrogen and phosphite. When you crisscross +1 and a -3, that 3 gets donated to hydrogen, so it's H3PO3. Writing names of bases, super easy. You name the cation and then just say hydroxide. So sodium hydroxide, magnesium hydroxide, lithium hydroxide. You do have to memorize ammonia. Remember, it's a Bronsted-Lowry base, but you do have to have it memorized. It's going in the opposite direction. If I give you the name and you need the formula, again, crisscross oxidation numbers. So potassium hydroxide. Potassium is +1, hydroxide is -1. You can just smush them together. Calcium hydroxide. Hydroxide is OH with a -1 charge. It's a polyatomic ion. So when you crisscross, you need to put the OH in parentheses with a 2 outside of it. Same thing for aluminum hydroxide. The aluminum is +3, so the little 3 needs to go outside of parentheses, so you're protecting your polyatomic ion, hydroxide. Lastly, we need to know the difference between strong and weak acids and bases and what makes them strong and what makes them weak. So strong acids and bases are acids or bases that ionize completely in aqueous solution to produce free hydrogen and free hydroxide ions. What we mean by ionize completely is that they break apart completely. So if you look at our picture right here, we've got hydrochloric acid and we pour it into water. So when we pour it into water, the hydrogens and the chlorines break apart. So we have separate cations and anions. They're no longer bonded. This means they have ionized 100%. So hydrochloric acid would be a strong acid because it is completely dissociated in water. If we look at our next example down here, we've got acetic acid where we've got hydrogen bonded to acetate. If we pour it into water, they only break apart sometimes. See, these are still attached, but this one has broken apart. So it's partially ionized, making it a weak acid. So realize what makes an acid strong is its ability to break apart completely when dissolved in water. It says here, any substance that ionizes or dissociates completely or almost completely in aqueous solution is known as an electrolyte. Solutions of electrolytes conduct electricity. So if we dip a light bulb connected to a battery into a strong acid or a strong base, it will light up because it is an electrolyte. Strong electrolytes are strong acids and strong bases and soluble salts. So things that are not electrolytes would be things like molecular compounds. And when they say soluble salts, think ionic compounds. Okay, so this list here of strong acids and strong bases actually does need to be memorized. So spend some time memorizing those. Strong bases are group 1 and 2 soluble hydroxides, meaning if the cation is the first 2 columns on your periodic table, it would be a strong base. It says acids and bases not on these lists are weak, meaning they ionize only a small amount. They're also weak electrolytes, so they don't conduct electricity well either. Okay, something worth talking about is concentrated and dilute versus strong and weak. I need you to know the difference. We're talking about strong and weak acids and bases. Again, we're talking about the level of dissociation. So this is something you have to memorize. When I'm talking about concentrated versus dilute, I'm talking about how much water is present. So it says, concentrated solutions have a large amount of dissolved solute and their molarity is greater than 1. A dilute solution has a small amount of dissolved solute and a molarity of less than or equal to 1. This is independent of the extent of ionization, so it has nothing to do with if it's strong or weak. Okay, so here are some examples. We can have a 1 molar solution of hydrochloric acid. The 1 molar part makes it very dilute. That means it's got a lot of water, very little actual hydrochloric acid. But what makes it strong is the fact that it's hydrochloric acid. It's going to break apart completely, dissociate completely when dissolved in water. We have a 12 molar solution of hydrochloric acid. Again, still strong because it's still hydrochloric acid, but this time it's concentrated because the molarity is higher. This means there's a lot more of the hydrochloric acid and a lot less water. Okay, to the right, I have a 1 molar carbonic acid. This is dilute because it's only 1 molar, but it's also weak because it is carbonic acid. It does not dissociate completely in water. We have 16 molar carbonic acid, still weak because it's carbonic acid, but it's more concentrated, meaning a lot more solute and a lot less water. Good example in real life of seeing dilute versus concentrated is when you're buying detergent at the grocery store to wash your clothing. You can buy the really small one here that says you can do 53 loads, or you can buy the larger one that also says you can do 53 loads. What's the difference? This one has less soap and more water. This one has more soap and less water. So high concentration, low concentration, high molarity, low molarity. This has nothing to do with its pH or whether it's a strong or weak base. It just has to do with the concentration. Okay, that concludes today's video. We have finished at the bottom of page 3 in your notes. I hope this was helpful, and I hope you got some real life application of acids and bases. If you have any questions, feel free to ask your teacher or watch the video again for a second time. Have a great day.